Will be by Michael Kozdron, and he's going to speak about a random walk proof of Kirchhoff's matrix tree theorem.
Okay, thank you very much for the invitation. So I wanted to just start with a few comments. So technically I'm actually Greg's last student from Duke. I graduated in 2004. Christian also graduated in 2004. We defended our theses on the same day, but he finished an hour before me. And I guess by alphabetical order, and by alphabetical order, he also received his diploma a few minutes before I did. So one thing about Greg is that when he hears a theorem, his first instinct is really to do the proof himself. And you know, he's really developed a number of his own proofs to many theorems over the years, and they're often completely different than the original. And Stefan alluded to this already when he was discussing Greg and his learning of complex analysis in the early days of SLE. And if you take a look, if you're familiar with the introductory part on conformally invariant processes on the complex analysis, you'll notice it's of a different flavor than what you'd find in the complex analysis books. And so I wanted to talk about one of my favorite proof of Greg's, and that's his proof of the matrix tree theorem. And as we go through this, if it all seems elementary to you and you're thinking this is really easy, that's sort of the point of this talk, is it is an easy proof. And in fact, there's nothing but undergraduate probability involved. And I'd actually say, please feel free to use this in your undergraduate teaching. So these slides. So this is based on joint work with Larissa Richards at Toronto and Dan Struck. And I also wanted to give a special thanks to both Greg Lawler and Shlomo Sternberg who encouraged us throughout this write-up. So some history here. Kirchhoff's matrix tree theorem, it gives a formula for the number of spanning trees of a finite graph in terms of a matrix derived from that graph. And if you were at Rick's talk, you heard him mention the theorem. And this really dates from the 1880s when Kirchhoff, who was motivated by problems arising from work on electrical networks, studied spanning trees. We jump ahead to 1979. Greg, as a graduate student, introduced loop-erased random walk in his PhD thesis. It was a model of self-avoiding walk, and he introduced it on the advice of his advisor, Ed Nelson, who basically said, why don't you try erasing the loops of a random walk? You told me that years ago, and I hope I got the quote right.
It's a correct paraphrase. I don't remember the exact quote.
Okay, so 96, David Wilson used cycle popping to prove an algorithm for generating uniform spanning tree. I assume everybody in here is familiar with Wilson's algorithm. We are going to review it briefly. But the matrix tree theorem does not follow directly from the cycle popping proof, and it's a proof of a very different flavor than what we're going to give today. 97 was the first edition of the book Probability on Trees and Networks by Lyons and Perez, which you may also be familiar with. The cycle popping proof of Wilson's algorithm is included in that book, and they use cycle popping to give a new proof of Cayley's formula. Cayley's formula is a formula for the number of spanning trees of a complete graph, but they do not include a proof of the matrix tree theorem. And in 99, Greg provided this new proof of Wilson's algorithm. I want to say it's via Green's functions. It appears in an article in the Kesten-Festschrift of Birkhauser volume, Perplexing Problems in Probability. I looked at the article again last night, and it does not mention the matrix tree theorem. 2010, Jeffrey Grimmett's book, Probability on Graphs, that's the IMS monograph, a red book some of you may also be familiar with. He discusses Kirchhoff's work on electrical networks. That's actually the first chapter, the relationship between random walks and electrical networks. His proof of Wilson's algorithm also uses cycle popping. And in Greg's book that he co-authored jointly with Vlada Limic, Random Walk, A Modern Introduction, there is a chapter dedicated to loop-erased walk. It includes this proof of Wilson's algorithm, and it does discuss the fact that the matrix tree theorem follows as an immediate corollary to the proof. As well, around the same time, Yves Legend's Markov paths, loops, and fields includes essentially this proof of Wilson's algorithm, but he leaves it as exercises to deduce Cayley's formula and the matrix tree theorem. These are very nice books, but they really are for a specialized audience, right? They're monographs in probability, and unfortunately, Greg's proof of Wilson's algorithm, it's not widely known or immediately accessible, even among probabilists. So So as Wendelin mentioned on Monday, when he was talking about news from the loop soup front, the idea of adding loops has really proved to be very, very fruitful for studying SLE and more. And many of us understand what these ideas of putting on the loops or taking off the loops or studying the loop soups can give you for more difficult problems. But when you go sort of right back down to the matrix tree theorem and to the very simple ideas of adding loops, you get to deduce this really nice result. And so our original goal, now maybe 18 months ago, was to give an expository account of Greg's proof, and turns out these ideas can be applied to deduce results from Markov processes. There's a discussion in Lawler and Limich's book about deducing results from Markov processes as well, but they're not quite the same as ours, but similar. So anyway. So I'm going to go through this quickly because it's really just to set up notation. This is the example I want to work with throughout. I've drawn it on the board if you just want to take a look at it. So gamma is a finite graph. I want there to be n plus 1 vertices because we are going to have one distinguished vertex, so there'll be n vertices left over. So there's n plus 1 vertices. We're going to label them y1 through yn plus 1. The graph's undirected, it's connected, and it has no multiple edges. It's easy to relax, but just adds more notation to everything. And since we're going to be concerned about spanning trees, we just want one edge anyway. And again, yi is similar to yj, or yi is nearest as a neighbor of yj if yj is in the edge set. So, okay, so the graph Laplacian matrix, just as a quick reminder, which I'm going to denote by script L, this is the matrix D minus A, where D is the degree matrix and A is the adjacency matrix. So I've written down for you the graph Laplacian matrix for this graph, and there it is. And you can see immediately which vertices are neighbors of each other and what the degree of each vertex is from that matrix. Okay, so Kirchhoff's matrix tree theorem. So by L super K, I mean the submatrix of L, which is obtained by deleting the kth row and the kth column. So LK is an n by n matrix. And the theorem of Kirchhoff's is if omega denotes the set of spanning trees of gamma, then all of the first minors are equal. Namely, the determinant of L1 is equal to the determinant of L2 is equal to ... the determinant of Ln plus 1. And that these all equal the cardinality of omega, namely the number of spanning trees of gamma. Okay, of course, practically this is very hard to compute, and the usual, let's say the usual modern way to prove the matrix tree theorem is purely algebraic. It involves the Cauchy-Binet formula. And there's a number of expositions of this proof that you can find on the web and in different textbooks. So this example that we're working with, I want to say you can check by hand that there's 29 spanning trees. And so I picked something that you could actually just work out if you wanted to. And for me, the easiest way to see that there's 29 spanning trees is just to figure out what the degree of y4 is in the spanning tree. So for example, if y4 has degree 4, then you can either include the edge from y3 to y6 or the edge from y2 to y6, and you get a spanning tree. So just by quickly checking it, you should find that there's 29 spanning trees in this graph. Okay, and again, just to illustrate the notation, if we take one of the let's say I picked 5, so we delete the 5th row and the 5th column from the graph Laplacian. It leaves us with this matrix, this 5 by 5 matrix. And if you wanted to check by hand, you could actually calculate the determinant of this. And this is the sort of exercise you give your undergraduates, and you just say, well, calculate the determinant of this 5 by 5 matrix by cofactor expansion or something, and you do that, and you find it's 29, and you do all the other ones, and you find they're 29 as well. So, okay, so random walk on a graph. So it's the usual thing. Simple random walk on a graph is obtained by moving equally likely to one of your nearest neighbors. And so I've just written down the notation. Pij is the probability moving from yi to yj. And it's 1 over the degree of yi. And of course, you can get the transition matrix just by looking at D inverse A. So, of course, this is what the transition matrix is for a simple random walk on this particular graph. Okay, so the graph Laplacian is D minus A. I factor out a D, and so I can write the graph Laplacian as D times the identity minus the transition matrix. And the notation that we're using is delta. So capital delta is a subset of the vertex set. It's a non-empty subset of the vertex set. And that is going to represent what is deleted. So that's basically where the random walk is going to end up, is in delta. And so L to the delta equals D to the delta, I to the delta minus P to the delta. That's the matrix obtained by deleting the rows and columns associated to the entries in delta. And I wanted to point out that, as you are no doubt aware, the fact that P to the delta is strictly substochastic, by which it means it has non-negative entries, the rows sum to at most 1, with at least one row sum strictly less than 1, tells you that I to the delta minus P to the delta is invertible. Okay? So that's standard facts. Okay, so the next bit of notation talks about the Green's function. And as you know, the Green's function for random walk is the expected number of visits to a site. So, is that a psi, I guess? I can't pronounce these letters or draw them, so you'll have to excuse me. Agilis? Zeta, okay. Okay, so zeta to the delta is the stopping time when the random walk enters delta. Okay, so it's the first time that the random walk enters delta. And for x and y not in delta, g sub delta xy, that's the Green's function that just counts the expected number of visits to y by simple random walk on the graph starting at x before its first visit to delta. Okay, so g, blackboard bold g to the delta, that is the matrix of Green's functions for all vertices that are not in delta. This right here. So G delta is the matrix of Green's functions. And it's easy to check that the matrix of Green's functions is exactly the inverse of I minus P. Okay? And the last bit here is R delta. That denotes the probability of return. So that's the probability that the random walk returns to X before its visit to delta. And you know that the Green's function is 1 over 1 minus the return probability. Okay, so G delta XX, the expected number of visits to X by random walk starting at X before entering delta, it's 1 over 1 minus the probability of returning. Okay, and let's now describe Wilson's algorithm. Okay, and so the idea here is that Wilson's algorithm generates a spanning tree uniformly at random without knowing the number of spanning trees. Okay, and you pick any vertex. Okay, this is going to be your target vertex V. Relabel the remaining vertices x1 to xn, whatever, and you start a simple random walk at x1, and you stop it the first time that it reaches V. So you do your random walk starting at x1, stop when it reaches V, you erase loops, and now you have a simple path connecting x1 to V. And you find now the first vertex that was not visited by what I'm calling the backbone, not the same backbone that we just heard about, but this loop erase walk path. And you start a simple random walk there, and you stop it when it hits the backbone, and you erase loops, and now you have a tree with basically 2 branches, and you repeat. Continually just going through, including these loop erased paths that join this backbone, and eventually you get a spanning tree. So it's clear that this algorithm generates a spanning tree, and so what we have to prove is that it's uniform among all spanning trees. Okay, and so anyway, I went to the trouble of doing an example just with our little graph here, and the whole business about relabeling the vertices, that's to write down the proof correctly and carefully, but of course it's much easier to understand it if you don't bother with that. So I picked a vertex that I'm going to stop at. I'm going to stop at y1, and I picked a vertex to start at. I'm going to start it at y2, so I do a random walk from y2, stop when it hits y1, and I erase loops and assume the loop erasure is exactly this. You know, it went from boom, boom, boom. And that's the first branch in my spanning tree, that's the backbone. I pick another vertex, say y3, I stop it when it reaches that backbone, and assume the loop erasure of that path was whatever it is, y3, y6, y2, and I add that branch to the spanning tree. And then I finally start a random walk at the last vertex y5. I stop it when it reaches the union of the 2 branches, and I add it to the tree. And so anyway, so there's our spanning tree, and what we've done here is we've generated a spanning tree with 3 branches. Okay, so the labeling, I just have to say what the three branches are: delta 1, delta 1, delta 2, and delta 3. Okay, so here now we're going to get to the main idea of how we prove Wilson's algorithm, and what it comes down to is just calculating the calculating a loop erased walk probability. Okay, so. So you just have to be careful that the notation is correct. So the idea is, give me a particular simple non-self-intersecting path that goes from x1 to xk plus 1 in such a way that the last step is into the target set. So I have this simple path from x1 to xk. The last step is from xk to xk plus 1. So that the notation works. And what we want to know is what is the probability that a simple random walk that the loop erasure of a simple random walk is exactly this. Okay? And that's exactly what this notation says. It says I start a random walk at x1. I define that zeta, C, that's a C, sorry, C delta to be the first time that the random walk's in delta. And I want to know what's the probability that the loop erasure of the random walk stopped its first time into delta is exactly this path. Okay? So the notation is much worse, of course, than the idea. And how do you compute it? Okay? So for the loop erasure to be exactly x1, x2, xk, xplay plus 1, what has to happen? The random walk has to start at x1. It has to make a bunch of loops back to x1 without entering delta. And then it has to take a step from x1 to x2. And then it has to make a bunch of loops back to x2 without visiting either delta or x1. Then it has to take a step to x3, and it has to make a number of loops back to x3 without either entering delta or visiting x1 or x2, et cetera, and finally it has to go from xk to xk plus 1. Okay, so you write that down. And it's just a bunch of geometric series, right? So again, the notation is worse than the idea. So that's telling me what's my probability of returning to x1 exactly m1 times. I sum over m1. I then take a step from x1 to x2. Then I have to start at x2 and return to x2 m2 times while avoiding delta and x1. I have to take a step from x2 to x3, et cetera. So you look at this sum of geometric sums, and you notice I have the product of the transition probabilities. So probability from x1 to x2, probability from x2 to x3, probability from xk to xk plus 1. The probabilities are 1 over the degrees, so that's this piece right here. Of course, sum of r to the m starting at 0, that's 1 over 1 minus r, and all it is just this notation. And so this probability is exactly the product of 1 over the degrees times this product of Green's functions, where the Green's functions are not for the same set, but for each time it's a set with an extra vertex added. Okay, so you've got this product of Green's functions, and now we just simply observe. So that was the probability of a particular loop erased walk path. Wilson's algorithm is obtained by doing this procedure, so you have a number of branches. So for each branch, you have exactly the same probability, or exactly the same idea to write down what the probability is. So suppose that I have produced several of these branches. So the probability that this particular tree was generated by the algorithm is exactly the product of the probabilities that these particular loop erased walk branches were produced. Okay? And let's plug everything back in. So because the probability are able to write it, the loop erase walk probability, as this product of Green's functions over the degrees. The probability that the tree is generated by the spanning tree is generated by Wilson's algorithm is exactly a product of Green's functions times this product of the degrees. Okay. So what is included in here is even though the notation is a little ugly, what we've captured is every vertex is in the tree exactly once. So you've got a product over all of the degrees in the vertex, right? Except for your target point. So you know what's the product of all the degrees. That's just going to be the determinant of the degree matrix. So I can see the determinant of the degree matrix already in there. And the proof is now completed just by using a very basic fact from linear algebra. And it turns out this fact from linear algebra is actually easy to interpret probabilistically as well. And so what I wanted to do here is I wanted to write down what the formula is going to be in the 2x2 and the 3x3 case, because you can see this, and you've probably done this exercise before, actually. And so remember, g delta xy is the expected number of visits to y by random walk starting at x. And here's the identity. So gxx gyy minus gxy gyx, you can write that as gxx g avoiding x yy. And everything is, of course, is happening before you enter delta. So that I haven't said the deltas, I've suppressed them. But if you notice, the left-hand side here, well, that's just the determinant of a 2x2 matrix. And this is a product of Green's functions where the sets are changing. And the way you prove this is you simply split the number of visits to x by random walk starting at x into two pieces. So you start at x, you're going to come back to x. Well, you come back to x without visiting y, you stop at your first time you get to y, and then you got to come back to x. And many of us would have done this as an exercise as soon as we saw Greg's Green Book intersections of random walks, if not earlier. And that's all that statement is. And you then realize, well, hey, you can generalize this. So in the 3x3 case, if I want to calculate the determinant of this matrix where I've written x, y, and z, well, how do I do it? I can calculate this. It's just gxx, g avoiding x, y, y, g avoiding x, y, z, z. Okay? And so there's a number of ways you can prove this. You can prove it by induction, sort of by finite induction, or you can realize it's actually just Cramer's rule. And so Cramer's rule is a way to calculate a particular entry in the inverse of a matrix. And I'm sure we all would have learned this in our first linear algebra classes, freshmen or sophomores or even earlier. And how do you do it? Remember, if you want the diagonal entry, if you want a diagonal entry of an inverse, well, what is it? It's the ratio of the determinant of the matrix formed by deleting the ith row, ith column, divided by the determinant of the matrix. And so if you just iterate Cramer's rule, you can conclude a formula for the determinant of the inverse given by successively deleting. You start by deleting the first row, the first column, then you delete the first row and the second row, the first column, the second column, and you continue. And of course, the order of which you delete things doesn't matter, so that's why you have to write it as this permutation. So I can start with the fifth, and then the third, and then the fourth, and the first, and whatever, and then you get it. But really, it's a way for computing the determinant of a matrix. Now, of course, this is an extremely inefficient way to compute the determinant of a matrix by computing matrix inverses. But the idea is this is the formula that we have. This is exactly the formula for this determinant of this matrix of Green's functions. So since we have some time, I wanted to do an example just to illustrate how you would calculate the determinant of a matrix this way. So here's a 3x3 matrix, and again, you can give it as an exercise to your students. How do you calculate the determinant of this matrix? You just do it, and you figure out it's 5/4. So I want some permutation, so I'm going to start by deleting the second row, the second column, then I'm going to delete the third row and the third column, then I'm going to delete the first row and the first column. And so I start by computing the inverse of M. So I calculated the inverse of that 3x3 matrix. And then what I do is I delete the second row, the second column. That leaves me with this 2x2 matrix. I compute its inverse, and I get this. And then I delete the second, the third, the second, the third. I'm left with that 1x1 matrix. and I compute its inverse, so I get 10/9. And so then what is the product of the relevant matrix entries? It's the 2-2 entry right there. It's the 3-3 entry, which is right there, and it's the 1-1 entry, which is right there. I multiply those three numbers together, I get 5/4. I get exactly the same thing. So that's the algorithm for computing the determinant of the matrix via this Kramer's rule. Okay? And that's exactly the proof. Because G delta is I minus P inverse. The graph Laplacian is, of course, the degree matrix times I minus P. So the determinant of this matrix of Green's functions, is exactly this product of Green's functions where you successively eliminate one vertex and then the second vertex and the third one, and you iterate that. And so the probability, remember, it was this product divided by the product of all of the degrees is exactly the determinant of the matrix of Green's functions divided by the determinant of the degree matrix, which is exactly some simple facts from linear algebra, is this is exactly 1 over the determinant of the matrix obtained by deleting the column and row associated with V. So the right-hand side of this equation, it's independent of the ordering of the remaining n vertices, right? So the only thing that comes into play here is your original target vertex V doesn't depend on the other n vertices that were left in the graph. So it tells you it has to be uniform. So you obtain exactly that 1 over the determinant of LV is exactly 1 over the cardinality of the number of spanning trees. Okay? And that is something I learned from Greg. Okay? And now you see that the matrix tree theorem follows immediately. 1 over the determinant of LV is 1 over the is 1 over the number of spanning trees. Cross multiply and you have it. And V, of course, was arbitrary. So that tells you that no matter which vertex you picked as your original target vertex, they all have to be the same. And so you conclude that all of the first minors are equal to the number of spanning trees of the graph. Okay, now this is something else that I think is really cool, because this gives yet another proof of Cayley's formula, which as far as I can tell is actually easier than every other proof of Cayley's formula that I've seen. So the formula might be a little bit different from what you kind of remember, because you're probably thinking n to the n minus 2, but just I have n plus 1 vertices, so the number of spanning trees is n plus 1 to the n minus 1, okay, just by the vertex count. And for example, the complete graph on 5 vertices, 4 plus 1 vertices, there's 125 spanning trees of that graph. So how do we do this? So let's just do the preliminary calculation. If we want to calculate a Green's function, it's 1 over 1 minus return probability. Well, how can we calculate a return probability? A return probability is just the probability of returning in exactly 1 step, plus the probability of returning in exactly 2 steps, plus the probability of returning in exactly 3 steps. And since our random walk is on the complete graph, it cannot return to x. It cannot return to its starting point in 1 step. It has to take at least 2 steps to get back to its starting point. So that's this thing right here. So the probability of returning to x is just the sum of the probabilities of returning in k steps, in k equals 2. Okay, so what do we have? We decompose our vertex set into 3 pieces. We compose it. I just want to make sure I have the right notation. So V1 consists of my starting point x. V2 is delta, and let's say the cardinality of that is m. And what's left is V3, and that has cardinality n minus m. Okay? That's why I did n plus 1. It just makes it a little bit easier to write. Okay, so what's the probability that you return in exactly k steps without visiting delta? I have to take a step from here into here. I have to take k minus 2 steps in here, and then I have to take 1 step back to here. What's the probability of that? I got to take a step into there. I've got to then take k minus 2 steps around in there, but because it's a complete graph, I only have n minus 1 minus m neighbors that I'm allowed to go to, and then finally I have to take a step back to there. That happens with probability 1 over n. Sum that up, I get this. 1 over 1 minus r gives me this. That's the Green's function for this particular random walk. And so we know that Kirchhoff's theorem is the determinant of g divided by the determinant of d. The determinant of d divided by the determinant of g. So I just have to calculate the determinant of g. But how do I calculate that? That is the product of these Green's functions where the vertex set's changing. So all I have to do is I adjust so that I successively delete one row, one column. So in the first case, I have one element in here that represents x1, the first row, first column. Then I have two elements in here, x1, x2, x3. And every time, so I have just set it up so that delta j is x1 through xj. The cardinality of delta j is j. So g sub delta j xj xj is exactly n times j plus 1 over j times n plus 1. I multiply this all out. I get n to the n over n plus 1 to the n minus 1. N plus 1 vertices. Each vertex has degree n. So what's the cardinality of this? Is just bang, and done. Okay? That's an easy proof of Katie's formula, I think. And the only idea was what's the probability of returning to x in exactly k steps. Right? So, okay. And anyway, this actually went a lot faster than I thought it was. So the last thing I want to say is I wanted to mention the results that we were able to derive from Markov chains. And this is actually a rephrasing of a theorem that's more generally given for Markov processes. And I didn't want to write down the Markov process theorem. It simply because it involves the Q matrix, which I guess is e to the TQ would be the transition semigroup for the Markov chain. And I really wanted to keep this just elementary to show you these ideas. And what you get is you actually get a formula for the stationary distribution of an irreducible aperiodic time homogeneous Markov chain. And when you're teaching this stuff to your students, what do you usually tell them to do? You say, well, solve pi p equals pi, right? And so instead of solving pi p equals pi, you actually just get to write down this formula for what the stationary distribution is. And so pi k is given by deleting the kth row, kth column of I minus p. And then you just, of course, sum over all of the different minors. And as well, you get a formula for a return probability. So I fix a state j. Row j is the first time after 0 that the chain visits j. So in other words, if the chain starts at state I, row j is the time of the first visit to j. If I does not equal j, whereas if I equals j, row j is the time of the first return to j. And so p sub p denotes the distribution of the Markov chain, assuming it starts at state I. So the probability of its first visit to j occurring before its first return to I is the ratio of these minors, where you obtain the first one by deleting just the jth row, jth column. You obtain the second by deleting I and j. Okay? And to conclude, here's a little example. So you give this to your students. You say, well, here's the 3 by 3 matrix, this Markov chain, calculate its stationary distribution. They all set to work solving pi p equals pi. You say, yeah, I can do this quickly. And so all you do is you look at I minus p, delete the first row, first column, you get this matrix. Look at I minus p, delete the second row, second column, you get this matrix. Look at I minus p, delete the third row, third column, you get this matrix. You can do these determinants in your head. So you get bang bang, you get 548, you go bang bang, you get 116, bang bang, you get 732. They're all common to 9060s, and so you right away you say, well, 10, 6, 21, so I get 1037s, 637s, 2137s. And you check solving pi p equals pi, that's exactly what you get. So it's a really nice formula, and this is in your book as well.
Well, no, the challenge is you gave a bunch of people the arithmetic to do for a bunch of exercises, which would be quicker?
This. Because I think so, because if you're teaching Markov chains to students, what do you always give them as examples to work out? You give them 3x3s. Or 4x4s, right?
No, but I do a 3x3, I did 5.
I don't know. I think it's because you don't have to solve any system. You just, you know, you're
It's close.
Rick, it's the same.
Equivalent to Healy's.
It,
Not Healy, but
it actually uses one less.
no.
Yeah.
You did 3 calculations.
Instead of 4. Instead of 4. You have to also have the sum up to 1.
Oh, but you snuck that in at the end.
Well, no, because
$37.
okay, because I looked at this. I had those 3 things together. I never actually also included the sum as 1. I just included the sum of these things. So. But what I claim is this is a formula you've probably never seen before, and that's sort of the point here, is that this is just a formula for the stationary distribution, which is somehow more explicit than solving pi p equals pi, subject to the sum of the entries of pi is 1. And as well, actually, let's write down. So what's the only, so 1 is not allowed to go to 2. So if you start in state 3, the probability of visit state 2 before it's first returned to state 3, you can write down what the answer has to be, it's that, but you can deduce this immediately just by looking at the Markov chain and writing down what the probabilities are. So if you're in state 1, you cannot move to state 2, you have to move back to state 3. And if you're starting in state 3, the only way to visit state 2 before you first return to state 3 is with this particular step, and that has probability 1/4, which was in this matrix. But if you start in state, if you want to visit state 1 before your first return to state 3, starting in state 3, it's a little more involved to figure out what that probability has to be. But you can write it down sort of directly from this formula. So anyway, you know, we were a few minutes early, but I think that's nice to give us a little bit of an extended lunch today and take our picture. So thank you very much.
Any questions?
Have you seen anything like that, Rick?
I was wondering if you're secretly just doing Gaussian elimination to compute the determinant, right? Sort of symmetric version of Gaussian elimination because you get the sequence of smaller square matrices.
So,
I mean, it'd be interesting to sort of see how the algebra fits in with the probability along the way.
So when I tried to write down the formula for the Gaussian elimination, I found I was using one less step here to do it. You know, I'm no expert on this stuff, really, so
There's a general meta theorem, is any linear algebra formula you write down, someone has found before.
Exactly.
There's no proof to that, but that's just...
So that's why I ask you, has anybody seen that formula for the stationary distribution before? Because I haven't, and I've looked in a few places. I asked a few people who, you know, Dan Struck had never seen it before, and he was one of the people I thought that would have seen it, so...
You know, if you look at I minus p and you're looking for something in the kernel, the left eigenvector.
Yeah.
So by definition, the left eigenvector is given by the sequence of minors.
Right.
Maximal minors.
Okay. Yeah. So there, thank you.
I'm sure it's equivalent to something.
It is,
It
but...
doesn't mean it's not a bad... It's a good idea to put it
Yeah, and exactly.
something like that as well.
But you know, like I said, my goal here was to give an expository count, and this is something I learned from Greg, and it was meant to illustrate sort of this general principle that, you know, he many times when he sees a theorem and wants to do the proof for it, he'll do it sort of on his own, and I think it's nice that people have seen this proof as well of Wilson's algorithm, because I don't think it's widely known, and just so you can now see how the matrix tree theorem follows from it. And anyway, so thank you.
More questions?
Group photo?